Moving on to Chapter 13, the Neurobiology of Sleep, we're going to cover sections 1 through 6. Okay, Section 1, Biological Clocks. Biorhythms are inherent timing mechanisms that control or initiate biological processes. These are typically linked to external cycles, such as the night-day cycle or across the seasons of the year. If you remember back to one of the early chapters, humans adapted in Africa, in the East Africa region, which is right by the equator. So we adapted in a more balanced night-day cycle, but we have adapted to living in areas where the night-day cycle is not as balanced. So in areas very far north, such as Iceland, the nights can be very long in the winter, the days can be very long in the summer, and humans have adapted to this. Although there are some drawbacks and issues that people experience. Even very simple organisms show biorhythms, indicating that this is a function of organisms that showed up very early in the evolutionary process. And biorhythms affect a lot of things, including blood pressure, body temperature, metabolism, sex drive, and hunger. Humans are considered diurnal, which means that we're awake during the day, and this is in contrast to nocturnal, which means awake during the night, such as raccoons or some cats. Biological clocks are guided by internal and external cues, and they prepare the body for upcoming expected events. So they prepare the body for sleep, drops in environmental temperatures that happen at night, for example, or with the seasons. There are different types of biological clocks. Ultraradian rhythm is a biological rhythm that lasts less than 1 day. So examples of this is like eating or activity. So we tend to have like rest, active cycles that cycle a few times throughout the day. Eating tends to happen 3 to 4 times in a day, or maybe 2 to 4 times in a day. Circadian rhythm is the day-night cycle, and this sleep is the prime example of this. The sleep-wake cycle happens once throughout the day and night for 24 hours. Circannual rhythm are biological rhythms that cycle over the year, over the 4 seasons. And this we see mostly in animals, so migration, yearly migrations, mating seasons, hibernation. And the circulunar cycle are biological rhythms that last 1 month, so 1 lunar cycle. An example of this would be in human women, the menstrual cycle happens about every 28 days. Human circadian rhythms actually lengthen in the absence of external cues, so a typical circadian rhythm would be 24 hours. With the absence of light or external daylight, this can lengthen to 25 to 27 hours. There's a German term called Zeitgeber, which means time giver, and this is any kind of external cue that helps to set these biological clocks. So a typical one would be light, another one might be temperature. The invention and popularity of artificial light likely has contributed to increased sleep issues in humans. It allows us to stay up and stay active after the sun has gone down. This probably has contributed to metabolic issues such as obesity and diabetes, as well as mood problems associated with difficulty sleeping and not enough sleep. People who work night shifts also have issues, higher levels of metabolic issues, again, such as obesity, diabetes, and this is likely because of decreased quality and time of sleep. Also, long-distance air travel can cause kind of insidious issues in the circadian rhythms. People who have bipolar disorder, which is actually strongly affected by sleep. So if the circadian rhythm is disrupted in people who have bipolar disorder, such as if there's a time zone change, this can actually trigger mood episodes, because it can trigger more typically mania, but also depression in people with bipolar disorder. And then long-distance relationships can actually cause circadian issues. So if somebody has a long-distance relationship where their partner is, say, up to like 6 hours different, there's actually some evidence that the person sort of emotionally is in that other time zone, and so this can cause issues with their circadian rhythm. Okay, and this is just some examples of disorders that can happen when biological clocks, particularly circadian rhythms, are not functioning normal. So there's delayed sleep phase syndrome, which is when somebody has a significantly later bedtime than what's normal, later than a social norm. And advanced sleep phase syndrome, where somebody goes to bed extremely early. And many of these things happening in clinical populations. I won't read through them all, but you're welcome to if you're interested. Okay, moving on to section 2, the neural basis of the biological clock. So in this section, there's a lot of detail that we could cover. I decided since we're doing 2 chapters at once, I'm going to go over some of the topics with more broad strokes, specifically the suprachiasmatic nucleus. So don't worry about all the details in the book unless that's something that you're personally motivated to learn about. The suprachiasmatic nucleus, or the SCN, is the main regulator of circadian rhythms. And this is a nucleus or a group of neurons within the hypothalamus. And if damaged, the sleep-wake cycle is very severely disrupted. That's how we know that the SCN is responsible for the sleep-wake cycle. Interestingly, the feeding schedule is not significantly affected, so the shorter cycle is not as affected, meaning that the SCN is probably very specific to this circadian rhythm, the sleep-wake cycle. SCN cells have actually like an intrinsic rhythm of activity, so just by the way that they're built, they are set like a clock, and the timing of this clock is mostly genetically determined, but there are external factors. So things like external light, things like that contribute to the entrainment of the SCN cells. Information about light comes from the visual system. The optic chiasm, which if you remember from the visual system, is where the nerves from the eyes, the optic nerves, cross over as they move back toward the visual cortex. While they're moving back, they also have some projections to the SCN, which gives the SCN information about whether there's light in the environment. The SCN cells are also influenced by physical activity and feeding cycles, and all of these things sort of entrain the SCN cells, so it's like setting a clock or setting your watch. Different types of people have different types of chronotypes. Chronotypes are varieties of circadian rhythms. So you might have heard like an early bird or an early lark is active in the morning, night owl is active in the evening, and there are actually both genetic and behavioral influences that determine chronotypes. So some people just cannot stay up at night. They have to go to bed by 9 or 10 p.m. Other people it's really hard for them to go to bed before 12 or 1 a.m. And while this might be influenced by some behaviors, some of this really is genetic. People can also differ in the length of their circadian rhythm. There's a pretty debilitating disorder where somebody has a significantly longer circadian rhythm than 24 hours, which means that they're going to bed a little bit later every single night. And that can be pretty stressful and pretty difficult to fight that urge if they're sort of set at a longer circadian rhythm. So the SCN functions as a pacemaker, which in turn entrains or directs what's called slave oscillators, and those slave oscillators control the functions that are regulated by their circadian rhythm. So slave oscillators control motor activity, different ones control eating rhythms, and then other slave oscillators control body temperature. The SCN projects axons to other nuclei in the hypothalamus and the thalamus, which connect to other areas of the brain and body. So SCN actually has a lot of projections and influences many different functions within the brain and body. SCN also connects to the pituitary gland, which regulates hormonal activity and also directly releases some hormones by itself, although most of the hormonal activity is through the mediation of the pituitary gland. And then the SCN also projects to the pineal gland, which inhibits melatonin during times of activity. So I'm going to cover melatonin in a little more detail later, but you might be familiar with melatonin because it can be taken as a supplement for people who want to entrain their circadian rhythm, people who maybe we're on the night shift and need to switch to the day shift, might take melatonin to kind of induce sleepiness. Circadian rhythms are also regulated by the SCN. So in animals, the SCN regulates mating seasons by controlling hormone release in the pineal glands. Shorter days means less daylight. Less daylight means less inhibition of melatonin, so it means more melatonin in the system. Melatonin inhibits sex hormones, and this leads to fewer reproductive activities. So it's very interesting, this connection between less daylight and fewer reproductive activities. The result of this is that animals who have mating seasons, like in the spring or the summer, for instance, are not reproductively active during the winter, during the fall, so they're not having babies that will be born in the winter, which would obviously, at least in areas where the winter is cold, this would be more dangerous for babies to be born during this time. Cognition and emotion also vary rhythmically. There's not a ton of research on this, but there is some data that, especially within the circadian rhythm, within the sleep-wake cycle, cognition and emotion vary. So, for instance, if you look at the top graph, there's some in the pre and post-adolescence. Adolescents tend to be different in general in terms of their circadian rhythms. If you know, like high schoolers and middle schoolers, they kind of tend to stay up later as opposed to the rest of the population. But for pre and post-adolescence, there's this morning tends to be a time of peak alertness with a dip right after lunchtime, and then it comes back up in kind of maybe the mid to late afternoon, and then steadily declines toward what is a typical bedtime. Emotions can also tend to occur at the same time each day. One example is this time in the mid-afternoon, sort of after lunch, when there's also this cognitive dip. There can be an emotional dip. People can feel a little bit down or grumpy during this time. There is an interesting study where people took data from Twitter, from UK Twitter accounts, and looked at, based on words that were associated with joy or sadness, looked at what time of day people were more likely to tweet things about, like happy tweets versus sad tweets. And so they found kind of, first, just this peak in general of tweeting. It looks like just a little bit before lunch, maybe at the 9 to 10 a.m. time. And then also fewer as the day gets longer, like more toward 9 p.m., fewer joy tweets as opposed to sadness tweets. So the comparison of these two, tweets could indicate, one interpretation might be that people in general are feeling a little bit sadder and a little less joy as the day goes on. Some psychiatric disorders might also include a bidirectional relationship with the circadian rhythm. So people with bipolar disorder, depression, schizophrenia, if they have an increase in the symptoms, mood symptoms or psychotic symptoms, it's likely to mess with their circadian rhythms. So for example, people with bipolar disorder, if they have a manic episode, if it's a serious manic episode, they're sleeping very little, their circadian rhythm is getting completely messed up, and then they tend to crash, go into a depressed episode, and might be sleeping for much longer, or paradoxically, other people with depression are not, also have difficulty sleeping during the night, or at least getting good quality of sleep. People with schizophrenia as well tend to do what we call like a day-night shift switch. So a lot of times when people are experiencing active psychotic symptoms, they're active during the night and sleeping. They're sedated during the day. So section 3, the section's going to differ a bit from the book. I prefer a slightly different, and I think maybe a little bit updated way to present the stages of sleep. So measuring sleep in general, individual differences are normal. Sleep differences are not a problem typically unless it's causing distress for a person or causing physiological issues. Some people only need a couple, like 5 to 6 hours of sleep. Other people need 9 to 10. Two main ways of measuring sleep, if somebody's having sleep issues, is just keeping a diary of sleep, as well as things that may influence sleep, like caffeine intake, napping, foods, things like this. And then EEG, a sleep study. And EEG is sometimes accompanied by measurement of the facial muscles and the eye movement, but typically just EEG is enough in a sleep study. Okay, so stages of sleep. To compare, awake, there's two general types of awakeness. There's being fully alert, and in this case the EEG is small amplitude, so the waveforms are not super high, not very tall, and it's high frequency, meaning the waveforms are close together. So this is 15 to 30 hertz, and these are called beta rhythms. In this frequency range, these are called beta rhythms. When somebody is drowsy, and typically when their eyes are closed, when they're feeling relaxed, the waveform becomes more rhythmic and also a lower frequency, so more space between the peaks and the troughs of the EEG signal, and these are called alpha rhythms. They oscillate at 7 to 11 hertz typically. In terms of the stages of sleep, sleep typically occurs in cycles of about 90 minutes, and within those 90 minutes there's two main types of sleep. There's rapid eye movement sleep, or REM sleep, and there's non-rapid eye movement sleep, or NREM sleep, or non-REM sleep. There's 3 to 4 stages of non-REM sleep. There used to be, I think kind of the old system is more that this conceptualization of 4 stages. There's a newer system where stages 3 and 4 are kind of pushed together, so either one is correct. For the sake of being consistent with the book, I'll talk about stage 3 as if it's stage 3 and 4, and let me know if you find that confusing. Okay, so in non-REM sleep, in which there are those 3 to 4 stages, stage 1 is the beginning of sleep. So there's slow eye movement, but the eyes are closed. These alpha waves disappear and are replaced by theta waves, which are a little bit slower, 6 to 10 hertz, and look something like this picture up here. People often twitch, their muscles twitch, and if the twitching is severe enough, they wake up, and a lot of times if you wake up somebody in stage 1 sleep, they believe they haven't been sleeping, so they're not even aware they've been sleeping. During this stage, during several stages, something called hypnagogic hallucinations can occur. Most likely during stage 1, hypnagogic hallucinations, as long as they're minor, are actually rather common, and this is hearing or seeing something that doesn't exist. So hallucination is perceiving something that doesn't exist. It's sort of like a mini dream. A common one is people will suddenly feel like they're falling and wake up. Another one is hearing their voice being called. That's a pretty common hypnagogic hallucination. And just to reiterate, these are very common. This is not at all a sign of psychosis. It's just a normal part of sleep. Stage 2 is slightly deeper sleep. Eye movements have stopped. Sleep spindles occur. Sleep spindles are these high frequency bursts, these little bunches of activity. And then in stages 3 and 4, which is, as I said before, has kind of been collapsed into stage 3 in more modern conceptualizations of sleep, this is deep sleep. This is what you hear like slow wave sleep. What's called delta waves occur, very slow, 0.5 to 4 hertz. And sleepwalking and a lot of other parasomnias or sleeping disorders that occur during sleep are most likely to occur during this phase. And then there's REM sleep. This is also called paradoxical sleep because the EEG in REM sleep looks surprisingly similar to wakeful EEG. If you look on this purple graph to the right, at the very top is wakeful EEG with this high frequency, low amplitude. And similarly in REM sleep at the bottom, you see this high frequency, low amplitude. There are distinctions. REM sleep tends to be more rhythmic than awake sleep, but they look surprisingly similar on EEG. So REM sleep is, of course, rapid eye movement sleep. It's characterized by rapid movement of the eyes. You can see the eyes moving underneath the eyelids. And vivid dreaming is more likely to occur during REM sleep. Dreaming can occur during any sleep cycle. It's a little more common during stages 3 and 4 and REM sleep, and you're more likely to remember it during REM sleep. Other indicators, physiological indicators besides EEG that somebody is sleeping, are decrease in metabolic activity, decrease in body temperatures, and then breathing and heart rate changes, even between the sleep cycles, tends to slow down as people get progressively deeper into sleep, although in REM it can speed up again. As people get older, the amount of sleep they need typically decreases, and the proportion of sleep that is dedicated to REM actually decreases as well. Many animals are able to maintain posture so they can remain standing, for example, during non-REM sleep, but muscle tone is completely relaxed during REM sleep in all animals. And you can see up in the right, upper right-hand corner, these are two PET images of a brain during non-REM sleep and REM sleep. You can see that the brain is more active during REM sleep, kind of consistent with what we see on the EEG. So dreaming is, of course, one of the most interesting aspects of sleep. We don't know much about dreams. Actually, we don't know that much about sleep in general. A lot of what we know is theories that can be difficult to substantiate. Dreaming, as I mentioned before, can occur in both non-REM and REM sleep. Dreams in REM are more vivid, more memorable, and we dream more often in REM as compared to non-REM. The longer we sleep, the more we do dream, so the further we get through the night, the more likely we are to dream. Almost everybody dreams, although many people don't believe that they dream. It's more likely that they just don't remember their dreams, so they wake up at a time that they're not remembering their dreams. And contrary to what a lot of people are, there's kind of a common myth that even if a dream seems to take course over 20 minutes, it actually happened instantaneously. It actually appears that dreams more often occur in real time. So if you dream an event happened over the course of 10 minutes, it might have actually been 10 minutes of dreaming. In terms of the function of dreams, again, a lot of this is rather theoretical. It's hard to substantiate and hard to test a lot of these things experimentally. The first person in modern psychology to really talk about dreams was Sigmund Freud, who's considered the father of psychoanalysis. And in Freud's view, dreams are representations of these unconscious wishes, and that we can interpret these dreams and get an understanding of people's unconscious wishes. As is the case with much of what Freud said, most scientists do not agree with this anymore. There's really no reason to believe this. Freud had poor methodology. He used his own patients as subjects, and Freud wasn't much of a, he was more of a philosopher than he was a scientist. So kind of in general, it's best to be very skeptical about Freud's theories. Another possible function of dreams is the activation synthesis hypothesis, which says that dreams are completely meaningless. They're just random firings that happen in the brainstem, then activate other brain areas that are involved in emotion memory, and so the brain, which is, our brain is always trying to make meaning of all our sensations, and so the brain kind of makes meaning out of these random firings. Another hypothesis is the coping hypothesis, which says that dreams help us prepare for life-threatening events. Evidence for this includes that the fact that dreams have mostly negative content, and this has been tested empirically. People are awoken while they're sleeping and asked about what their dream was, and most dreams have negative content. As well, scientists have noted that in dreams, when somebody is faced with a threatening situation, they're more likely to approach So in the like fight or flight reflex, they're more likely to fight as opposed to avoid that threatening behavior. And so the idea in the coping hypothesis is that we kind of practice dealing with threatening situations through our dreams, which is kind of a safe space. Lucid dreaming is an interesting phenomenon you might have heard of, and this is dreaming in which one is aware that they are dreaming and they can control the dream to some extent. So if someone is having a lucid dream, they might be able to decide that they're going to start flying in the dream and then fly. And they know that it's a dream, they know it's not real, but they can kind of imagine or control the situation, sort of like virtual reality. Lucid dreaming may, the difference between regular dreaming and lucid dreaming may be the activation of the dorsolateral prefrontal cortex, which is this area of the prefrontal cortex that's involved in working memory, as well as kind of other executive functionings. So there's some indication that that might be active during lucid dreaming, but not active during the rest of REM sleep or regular non-lucid dreaming. Lucid dreaming might also be associated with micro-awakenings, so people might be waking up quickly, then going back to sleep during lucid dreaming, and so kind of walking that threshold between awake and sleeping. And preliminary studies do indicate that teaching lucid dreaming can be used to reduce nightmares in people who have very severe and debilitating nightmares. I haven't tried this, and I haven't looked too much into the research, but it does appear that you can train yourself to lucid dream. And it's surprisingly a bit similar to some techniques that were used in that movie, what's it called, Inception. So if you're interested, you can look at this YouTube link, and there are other resources online, but they all have the same general strategy, which is sort of a reality testing strategy, that you teach yourself while you're awake, and then kind of get it in your brain enough that it might show up when you're dreaming. Okay, so moving on to section 4, what does sleep accomplish? We actually don't know for sure that much about why we sleep, evolutionarily why we sleep, but we have some ideas. So sleep appears to be a biological adaptation. We save energy during sleep, during the nighttime. We can't, as diurnal animals, we can't forage for food or move around easily during the nighttime, so it makes sense for us to sleep and save energy. Evidence for this is pretty clear data that indicates that predators sleep longer than prey. Predators can afford to sleep longer than prey because they don't have to be awake and alert, at least as much as prey. There's also basic rest activity cycle, the basic rest activity cycle, which is cycles of 90 minutes in humans. And these 90-minute cycles appear to be present in both sleep and wakefulness. So as we covered just a couple slides ago, the sleep cycles, the 3 to 4 non-REM cycles and the REM cycles tend to occur in 90-minute intervals. And our day cycles also happen to occur in 90-minute intervals. So we tend to have like activity rest cycles that occur in these 90 minutes. Sleep appears to be restorative for our body and our brain. And this evidence comes mostly from looking at what happens when people don't sleep. So acute, extreme sleep deprivation can lead to pretty serious cognitive problems, memory and attention. It can lead to mania, even in people who have not previously had mania. So sleep deprivation can actually lead to an inability to sleep and kind of hyperactivity. It can lead to hallucinations, seizures, heart problems, and proneness to accidents. When people are deprived specifically of REM sleep, when they're allowed to actually have REM sleep later, their REM sleep becomes longer, and this appears to indicate that the body needs REM sleep because it's kind of compensating for that deprivation of REM sleep. Antidepressants can suppress REM sleep, which might be one reason that people tend to be a little more groggy when they're on antidepressants. Just a quick note at the top about a typo in your book. We're going to cover memory in a later chapter anyway, and I'm not going to get too much into memory before then, but just if you were confused by that typo, there's a quick clarification. Alright, so the role of sleep in memory storage. There's been quite a bit of attention to the role that sleep plays in specifically the consolidation and recall of memory. So memory improves after sleep. The brain areas for functions that are learned before sleep are activated during sleep. So if people learn a motor task repetitively before they sleep, and then their brain activity is recorded while they sleep, those areas that were used during the learning of the motor activity are activated during sleep, indicating they might be sort of encoding or doing something with that memory during sleep. There are three main phases of memory. There's the labile phase, where memory is kind of like briefly encoded, but it's not permanent in the brain yet. And then there's consolidation, where memory is stored permanently, and recall, where memory is brought back into conscious awareness. And those latter two phases of memory are implicated in the sleep process. So theories of memory function in sleep, there's actually a lot of them, but some three common ones are the multiple processes, which is the idea that different kinds of memory are stored during different sleep phases. In the sequential processes theory, different stages of memory consolidation and recall occur during different sleep stages. In the storage process theory, waking memory functions continue in the same brain areas during sleep. The advantage is that memory functions don't have to compete with other waking functions, so it's kind of a time when memory can take over the brain and do a lot of its work while somebody is sleeping. Interestingly, marine mammals, including dolphins, whales, orcas, porpoises, have unit hemispherical slow-wave sleep. So that means during non-REM, during that 3 to 4 sleep phase, one hemisphere of the brain remains awake while the other one sleeps. So they sleep one hemisphere at a time. And the eye contralateral to the awake hemisphere remains open. So they literally sleep with one eye open. This is likely in part because they have to maintain some postural control because they are underwater. They can't just lose all muscle tone. And for this reason as well, they may not have REM sleep. REM sleep is associated with a complete loss of muscle control and may not be adaptive for marine mammals. Okay, so section 5, the neural basis of sleep. Again, I'm going to deviate from the book a little bit in this chapter. The induction and maintenance of sleep involves quite a variety of brain areas, different hormones and neurotransmitters. We're not going to cover it exhaustively. I'm just going to cover the main ones. So one of the main areas is the reticular activating system, or the RAS. And this is also known as the reticular formation. So our reticulum is a large group of cell nuclei and nerve cell fibers. The RAS runs through the center of the brainstem specifically, and it projects to the hypothalamus, which in turn projects to other areas of the brain. Sensory stimulation creates wakefulness by stimulating these RAS neurons in the brainstem. Brainstem damage can be very serious and often leads to coma, and this is in part due to the RAS. If somebody has damage to their RAS, they can't be awakened. They can't be stimulated into wakefulness. Many neurochemicals are involved in sleep, and we actually don't understand a lot of the complex processes that these are all involved in, but many of the monoamines, norepinephrine, dopamine, serotonin, are involved. But I'll just kind of mention some of the main actors. So cortisol, levels of cortisol rise before waking and kind of peak right after we wake up, and then decrease in the evening, slowly rising again, starting in early morning if you're someone who has a normal sleep schedule. Serotonin converts to melatonin in the pineal gland. Melatonin likely promotes sleepiness. The exact function is not totally clear. If you've ever heard of tryptophan, this is a compound that there are high levels of tryptophan in many protein-based foods, such as I think fish and egg whites. So tryptophan converts to serotonin, which converts to melatonin, which you might have heard that tryptophan induces sleepiness, and this is the process by which tryptophan induces sleepiness. There's a myth associated with Thanksgiving that turkey's really high in tryptophan, and that's why you get sleepy after the Thanksgiving meal. This is actually not true. Turkey's not particularly high in tryptophan, and unless you're eating like a huge plate of turkey, it's more likely that you're just eating a ton of carbohydrates, which convert to serotonin, and also just overeating in general makes people sleepy. So unfortunately, it's not the turkey. You can't blame the turkey. It's just overeating that's making people sleepy. Adenosine is a compound that we covered just briefly in the hormones and neurotransmitter section. It's a natural byproduct of energy use, or ATP, in our cells. And throughout the day, as we use energy in our cells as ATP is used, there's a buildup of adenosine that creates a pressure to sleep, or an inhibition of wakefulness. If you remember, caffeine is an antagonist of adenosine. So caffeine suppresses adenosine, which helps us stay awake. Section 6, sleep disorders. There's actually a ton of sleep disorders, but I'm just going to cover some of the more common ones. There's, well, I'm going to cover one rare one first, which is fatal familial insomnia. This is a genetic condition where a specific protein creates a compound that builds up in the thalamus, and it's a genetic condition, so it's completely determined by genes, where sleep is completely inhibited, and because of this, if there's no treatment, the individual dies after several months of not sleeping at all. Sleep disorders that affect NREM cycles include insomnia and narcolepsy. Insomnia is a prolonged inability to sleep. There are many different types of insomnia. This can be affected by psychological disorders such as anxiety, depression, or mania. It can also be affected by lifestyle, drinking too much caffeine. Kind of a dysregulated circadian rhythm can also cause insomnia. Narcolepsy is when one uncontrollably falls asleep in the middle of what would typically be wakeful periods. So it's typically 5 to 10 minutes of unexpected periods of sleep. One possible cause of narcolepsy is sleep apnea, which is disruptions in breathing while sleeping, which can cause very poor sleep quality. So sleep apnea can be very, very scary. It can be caused either by the central nervous system or by problems with the sinuses and upper nasal cavity. But people can breathe as little as 4 times in 6 minutes, which you can imagine kind of creates a lot of stress on the brain not having oxygen during those times. REM sleep disorders can be even more bizarre. So one particularly scary one is called sleep paralysis. And this is atonia, which again is complete lack of muscle movement or muscle control, and dreaming while a person is awake. So a person cannot move, they're awake, but they're also dreaming. So they're aware of things moving around in the room. If somebody comes in the room, they'll perceive that to some degree, but they might also perceive that there are demons. It's usually negative things that people with sleep paralysis are perceiving or dreaming about. It has about a 7% prevalence in the general population, so surprisingly large number of people have experienced it. The people that your book mentions that in a student population about 30% experienced it, and I'm very skeptical of that. I wonder if people were misinterpreting the meaning of sleep paralysis. It didn't sound like a very scientific survey. 35% of people with panic disorder actually experience it. So people with panic disorder is surprisingly somatic. It's can be caused by an overinterpretation of somatic symptoms, and people can have panic when they sleep. They can wake up in a panic disorder, and so associated with this is sleep paralysis. Cataplexy is atonia, or inability to control muscles, associated with REM sleep that occurs when a person is fully awake and active. So it's a little bit different than sleep paralysis, but they can co-occur. So cataplexy can be sudden or gradual. Somebody can gradually slump down, or just sort of collapse. And this is usually triggered by an extreme emotion, so laughing, crying, fear, embarrassment, surprise, and it's rather common in people with narcolepsy. A lot of these sleep disorders occur together, so if one person has one sleep disorder, it's much more likely that they're going to have another one. Finally, there's REM, or REM sleep behavior disorder, also called REM without atonia. And this is, without atonia means that the muscles are active, and in this, people during REM sleep act out their dreams. So behaviorally enact their dreams. If they're throwing a baseball in their dream, they might actually make that muscle movement while they're sleeping. Sounds like it could be kind of dangerous to anyone sharing the bed with them. Treatment of this includes blocking REM sleep with benzodiazepines, which you can imagine could significantly decrease the quality of sleep that the person is getting and might have some effects on their life during waking hours. Okay, and then just a reminder, section 7 you don't have to read. By all means read it if you would like, but I won't be covering it in homework or the exam.